Hello, my name is Roberto Lublinerman. I'm an engineer in the WIT team at Google. I've been working for the past 2 years improving the compiler, and I'm going to just talk about that, dump a bit of my knowledge, and hopefully entice some of you to contribute to the compiler and work on it. So the overall architecture of WIT is two things. It's a compiler from Java to JavaScript, and there is all the libraries that allow you to write applications against in the web that are packaged like as libraries, and there is some bootstrap code that gives you options on how to run your applications. And it's not part of the libraries per se, because it's basically template code that maybe it's part of the linking process. So the main focus we're going to do in this talk is the architecture of the compiler. We're going to look at what are the passes that we do to the code. We're going to look at the internal representations that we keep. We're going to see how the optimizations work. And we're going to try to help you understand how we process your Java code to compile it into JavaScript. So the compile, per se, it's divided in 3 parts. It's organized in 3 parts. There's one that we call the precompile. There's the compile proper, and there's the link. The precompile basically is the phase in which we load the modules, we discover all the Java files, the Java source files that we need to compile that application. We discover what the properties are defined. We decide what are the bindings for the GWT creates, and we perform a Java compile on all the Java classes. And the output of this stage of the precompile, it's a huge AST that represents your Java program, but the whole Java program, all the classes that are, even more classes that probably are actually going to be used at the end. So this is kind of an initial view, a very big Java AST. And that AST then will be optimized, will be translated into JavaScript, and it will be packaged by the linkers for use as an application. So the interesting part here is the center, which is called unify. So there are many stages in this precompile. Basically, we read the module, you pass a module on the command line, we read that one, we go look in the class path for all other modules that are inherited. We also find the source code in the class relative to all the entries in the class path. If Java classes are repeated, the first one that gets mentioned somehow wins, but if there is super sourcing, that takes priority. We used to allow you to load precompiled libraries. This is going away because it doesn't seem to be a big, it's not a big improvement, and it's a simplification not to have it. Then we look at all the properties that are defined, all the rebinds. We compute what permutations are needed for the compile, and what are the values of the properties for each permutation and the rebinds. We collapse permutations that have the same properties and same rebinds. And the important part is the next one, which is it's called the unify AST. So this one, we get all your entry points, which can be defined by you in your module, or it can be defined in the libraries. So all the entry points that are declared and accessible from the module def are traversed in the unify AST. And every class that it's reached, it's stitched into the big AST. Basically, only methods that are actually reached are explored. So it's kind of already there is some sort of pruning around. And during this phase, whenever you traverse a method that has, for example, a with create, That's where we run the generator and mark that place as being provided by some rebinds. Once the generator runs and produces code, the code gets compiled and gets, again, unified. And at the end of all that, we get a huge AST representing the Java program. Then we extract some information. We compute, for example, the full hierarchy, the overloads, and we perform some fixes. For example, we decide, there's some things that we implement different than in Java. For example, the get class and the class literals. So we have a pass for that. So we remove assertions. There are some things that we do in these pre-optimization fixes. We do an optimization to trim unnecessary code but this is with all the AST, not permutation specific. We record all the rebinds and we go to the compile, which is where I'm gonna focus most of my talk. So once we get that big AST and we have the permutations, we invoke the compile for each permutation. So optimized compiles are permutation specific. So the first thing that we do is we replace all the rebinds, all the with creates that might be bound to multiple implementations. Once we get the permutation right, then we just replace it by the actual class that needs to be rebound there. Or if it's collapsed in soft permutations, it can be a procedure that decides how to create classes for that particular rebind. Then we run the optimized loop, which the main purpose of our optimizations is to prune the AST. It's to reduce the code size. That's the main focus. After we get the optimized program, we normalize it. We implement the casts, implement the long emulation, everything that is implemented in JavaScript. All the Java features that need to be implemented by library code in JavaScript, they basically are handled in the normalization pass, and then we generate JavaScript. On the other end of the spectrum, once we get, so now this is the second AST that type of AST that we have. We have the Java AST, and then after compilation, we have a JavaScript AST. And that again goes through several phases. First, we normalize. Basically, the JavaScript AST that's produced by our transformations is not, if we print it as a program, it's not really a valid JavaScript program. So the normalizer takes care of that. We decide the identifiers, what do they point to. We optimize the JavaScript. We perform code splitting. We do some fix-up passes, and we rename for example, if you're running obfuscated mode, that's where we obfuscate all the identifiers. And that's the code that's produced by the JavaScript compiler and gets handled to the linker for the next phase. So the first AST we encounter is the Java AST. This is basically the main classes of it. So every Java AST node, it's a subclass of node. And the main classes there are JType, represents a type. It can be either a primitive type or a class or an array or an interface should be also around here. We have variables, we have three types of variables: the fields, the locals, and the parameters. Then the statements, so that is a big tree. So we have all this, that will be the superclass for all the statements. The body of the method, we have two types of body. It's like the normal Java, the ones you wrote in Java. It's a method body. We would have a block in a list of statements in the block. And the GSNI method body, which is JavaScript code that you wrote in your Java class as a native method. And that will be that will be in the GSNI, there will be an instance of GSNI method body pointing to a JavaScript AST. And expressions, well, methods will contain, contain a method body, one of those. And then expressions, which are inside of statements, also the full set of expressions, binary expressions, unary expressions, the cast operation, the instance of, all these are expressions in Java. So this is basically a big view of the Java AST that the WIT compiler uses to handle, to manipulate Java programs. It's not here, but it's not completely Java. So if you go from this and you get the AST, you print it, you will have something that's not really a Java program because, for example, one of our expressions is a multi-expression. It's a sequence of expressions, mimicking the one that's in JavaScript. So there are some things that are not really Java, but it's the representation, the view that we have over Java program that's useful for us to perform the transformations. So here, for example, there is the representation for a class that has a class foo, that has an field, which is an int field in a method. And as you see, you have a node of class type, and that would have, as members, it would have a field and a method. And the method would have a body, the body would have a block, and the block would have one statement, which is an expression, and which is actually it's a binary expression that has two sides. One side, it's a field reference, and the other is the actual operation. And the interesting thing is that the AST, you notice I used two different type of arrows, like the solid and the non-solid, let's say, arrows. The non-solid, basically, if you look at the solid arrows, every node has only one incoming arrow from the AST, and that's what's used for the traversal. Traversal passes will follow these solid arrows. But entities like a field reference, like the X on the left-hand side in bar, which refers to the field X, will have a pointer to a field node, which is not traversed explicitly in a visitor, but you could access it while handling the operation or the field. And the same thing for types. So types, whenever there is a type, it will be a reference to the actual node, the actual node in the AST tree that represents that type. So this will be the field reference, there will be the types, and then there's the method calls. That's the same. If there is a method called, there will be a reference to the actual method in the AST tree, which does not mean that's the method that gets actually called because of dynamic dispatch, but it's the method that's resolved at that location. So typical optimization or transformation in the WIT compiler, you start from, you extend visitors. So there are two base classes for visitors. You have the JVisitor class that is meant to traverse the tree but not modify it. And it's used for, normally, some passes perform first collection of data, and then they use that data to modify the tree. Some passes they do both things with the same visitor. Depends on the complexity of the pass. So if you want to do a transformation like this optimization, you just extend the JMod visitor, and that one would have end visit. You can override an end visit for the particular node that you're interested in modifying. So in this case, this is a constant folder that only cares about binary operations. In particular, only does addition. So when the visitor gets to the binary operation over there, it matches. It makes sure that both sides are literals. Because if they're int literals, that means that there are integer constants. And then it creates a new node to replace the binary operation that, that basically it's again a literal that has the value, the computed value. And one thing that's important when you're writing passes is every node has attached one thing that's called the source info. Basically means where did this node came from in the original Java source. For example, that binary operation would have comes from some line, some file, some line. So basically, you want to preserve that information so that when you generate source map for the Vaadin, you can step in the right places. So in this case, after applying the optimization, you get the transform tree that has the binary operation replaced by the computed value. So during Java optimization, sometimes you need to query to query things about your program, and there is this object which is a type oracle, J-type oracle, that resolves those queries. And you can query, for example, what are all the subtypes of a class, what are all the interfaces, what are all the overriding methods of a method, what is the effective class initializer. For example, if you have several classes and only the top one superclass has an initializer, and you ask in a subclass, it tells you, okay, so if you want to initialize this class, you only need to initialize the superclass, for example. It keeps mappings, so when we devirtualize methods, we need to know which method devirtualized which call. And it can answer questions, casting from A to B, does it always succeed? Does it always fail? So this is very useful for optimizations. And across, when we're in the optimizing part, we have we merge the analysis information right back into the AST, which might sound complicated at the beginning. So for example, I'll show an example later. But so we have analysis types, like if you discover that a variable is always null, we replace its type and say, oh, so it's this, the type of this variable is a null type. Or if we discover a variable is never null, then we say, oh, this is a non-null type. Or if we discover that the variable can only hold object of a specific class and no subclasses, and it's not null, then it's an exact type. And I'll go over that in more detail. Keep in mind, have many things that are called oracles in WIT. There are the type oracle that's used by the generator. This is not that one. This is a different one. This is the J-type oracle. So we have these optimizations that we run, and we run in a loop. Every optimization does a very little transformation that's useful for the next one to kick in. And that's normally the way you write optimizations in a compiler. You do small transformation. Every little pass does a small transformation that exposes other opportunities for other optimizations. So the first one that we have is called the pruner. So this basically traverses the control flow graph of the whole program, starting from the entry methods, and gets rid of unreachable method classes and fields. The interesting thing about the control flow algorithm that we use is that it discovers, while traversing the methods, discovers which classes are actually instantiated. So it computes at the same time the reachable methods and fields and the classes that are instantiated. And that allows you to trim, like, that's one of the most effective control flow analyzers that you can use in this type of languages without having to pay more cost. So adding more precision doesn't give you much more results. So this is an example of a simple pass. This is a finalizer. Basically, it traverses the tree trying to see, because you now see the whole program, you can see which classes are actually final. So every class that's at the bottom of the hierarchy, you can mark it as final. every field that is never mutated, you can mark it as final. Every parameter, every method that's not overridden, you can mark it as final. And you can use that information that you already stored in the AST in a different path to perform other optimizations. So this per se doesn't do much, but it marks for other passes. So the next one, the name of the class is makeCallStatic. It's the gvirtualizer. And basically, it goes through the whole program looking at method calls. And at each method call, it just looks whether this method call, if it goes through instance method calls, and it just looks if that it's actually a static dispatch in the sense that there is only one possibility at that. It's already been marked as a static dispatch, let's say. That's marked by another pass. And if it does, then it rewrites the method. So the first time it rewrites the method to make it a static method of the class. It adds a new parameter at the beginning. So when you're debugging with code, you probably found, if you debugged in JavaScript, you saw these methods that start with $, and they have an extra parameter, which is the implicit this parameter, which is made explicit. And then it rewrites the call to be a static call. And this is pretty useful, because if you only, for example, use one method of a class, and you don't use any instance, you may have just the right code. It's static, you might inline it later, and then you don't need to keep the code for the rest of the class. So this is one of the optimizations. The next one is the type tightener. Basically, this one is that one that tries to decide for every single entity in the program, what's the best type. We try to find a way to describe what are the objects that can be on in that entity, or see if it's a variable, you want to see what are the types of the object that can be actually in the variable. If it's a return type, what is the actual objects that are returned? And this is the pass that goes through the program and does this transformation. For example, if you have like object O equal new foo, after this pass is run, it will decide that O only has foo assigned to it, so let's record that the type of O is foo in the variable. And this by itself doesn't seem that it does much, but allows you to virtualize later. So the method called tightener, it's held by the type tightener as well. And basically, when a call is recorded, for example, here the x.add. So here you have an array list in a variable x, and you call add. And the type of the variable is list. So when you first get the EST, it will tell you this dispatches to list add. But if we type tighten to array list first with the type tightener, then when we look at the dispatch, because the actual type of the variable recorded here, it's array list, then we can make a more specific call. Instead dispatching to list.add, we now think that we dispatch to array list.add. And yeah, so and this eventually will, in this case, it will turn to be a static dispatch, because it's exactly array list. So we know exactly which is the method that needs to be called and can be transformed into a static call. So dead call elimination. So this is a pass that performs what's known in compilers as constant folding and propagation and static evaluation. And dead call pruning. That's three things. So for statements, it prunes things that are unreachable. For expressions, it tries to evaluate statically constants. Also can evaluate statically string operations. For example, if you do string equals and you have two constants, then the compiler will just perform the comparison and replace with the result of the static evaluation of that comparison. So if someone wants to look at the compiler, dead code elimination is kind of one of the nicest passes to look at because it's a local optimization, so you can see how it works. It has many, many, many cases, so it's one of the easiest to get into. The inliner. The inliner in the Java IST, it's called the method inliner. It's a very dumb inliner. And the reason why it's dumb is that inlining is really, really good for performance. But it's not so good for code size. So there is a trade-off because if you inline, then other passes might see things to prune. So it might get better types. You might benefit from it. Even if you increase the size at the beginning, you might benefit. But sometimes you don't know that until the pass is done. So you have to make a choice of what to inline. Ours, it's very simple. It tries to inline only very small fragments. So this we probably need to work. That's one pass that I'm sure it'd be benefit if someone looks at it to improve it. Then there are specific passes like the enum ordinalizer. So if you have some enums that are used just basically as integers, then we replace them by integer. Yeah. But if you use them like you put virtual method on it, and then no, we don't. So this is actually good if you have a lot of enums that you use as integers, because otherwise each enum is a class, and sometimes each enum instance, each value instance, it's also a class. So that's the Java model. And the last one, we call it the same parameter value optimizer. But basically, this is it's a very limited form of specialization. Basically, if all the calls you find in the code, because you see the whole program, have some parameter value that's a constant and it's always the same, we specialize the method for that constant. So we propagate the value inside the method, we remove the parameter. I don't know how effective is that one. It seems it's effective if you have that kind of pattern. So here is how they work together. So you have this very simple program. You have an entry point that creates an object of class bar and calls M1. And you have two classes. One is a subclass of the other, and an interface, and only one method that's declaring the interface and implemented and overridden in the classes. So if we first run the finalizer, yeah. So they're not my mistake. So they're not subclasses. They're just they just implement interfaces. So we run the finalizer. We detect these classes don't have any subclasses, so they are final. We detect that these methods are not overridden. They can be marked as final. The entry point can be marked as final as well. Second pass, type tightener. So when we go through the method, in this small example, we find that method that said that foo equal new bar. So the type tightener discovers that foo is only a signed object of type bar, and marks that by changing the type of the variable foo. But notice that the call says, so I'm calling M1 on foo, but this M1 points to foo M1, not to bar M1. And that's changed by the method called tightener. The method called tightener realized that you're calling M1 on a bar object, so it can specialize that, get a better override for that. Then the virtualizer now realizes, okay, so that was a final method, so it's a static call, so we can devirtualize it. So we create M1, $M1, which is the static version. It has an implicit, it makes explicit the first parameter, which we always call it this $static. We replace the call because that call was static, so we can replace the call. We replace the the contents of M1, which in this case was empty, but the virtualizer doesn't look at that. So it will insert a call to this new devirtualized method, so that the method body it's not repeated. And next we run the pruner. So in the pruner we detect, oh, there are only objects of type bar, so bar, gone. There are no calls to M1, so M1 gone as well. And then we run the inliner. So this runs in a loop, so I'm just running them arbitrarily in arbitrary order. So here we run the inliner. M1 foo was as an empty body, so we inline it. That's one of the ones we know how to inline. It gets inlined, and then next time we run the pruner, it's gone. I think I missed. Well, next time we run the pruner, M1 will be gone because there are no calls anymore. And that's basically the way we trim the AST to get the smaller possible Java AST to which to translate to JavaScript. So most of the interesting work is done by the type tightener, which determines that it basically determines some idea of what types can inhabit variables, parameters, return types. And basically, there are these distinctions. If it's marked like by a specific, like a class type or an interface type or a primitive type, it means that this entity will have that type or one of its subclasses. Or it can be null. And so in the next example, we're going to note this as if the class type was A, we will note it as like A. If we determine that that object can never be null, then we'll assign it a type of a J non-null type class that will point to a type. So it would say this is a J non-null type of class A or of interface B. And what that means is that that entity can be an object of that class or any subclass, but not null. And we will denote it with a bang in the examples. If we determine it's a null type, then we will replace it by J null type, and we'll denote it as null. And if it's an exact type, we will replace it by J exact type. And that means that, and of some specific class type or interface type. And that means that that entity contains exactly an object of that class, that it's not null, and it's not a subclass. And we'll call it a numeral in the example that follows here. So let's say we start with this program, in which we have these 4 variables, A1, A2, B1, and B2. And if we look like, for example, A1 gets only assigned new A. So this would be an exact type of A. But A2 gets assigned A or B, and B is a subclass of A, so that would be still the type A, a non-null type A because it cannot be null. And similar for B. So for B1, it's only assigned null, so we'll change that to null type. And for B2, it can either be null or B, so it returns the type B. So there we lost a little bit of information. Here we could say that it's an exact type or null, but we don't have that abstraction in the compiler. So, but the interesting thing is that once you do that, then, for example, if you find a comparison that says B1 instance of X, then we know it's null, so we know that's false. That's how other passes benefit. Or for example, in the first one that it's A1, it's an exact type. So if you do A1M, then you can actually replace that by a static dispatch because it's exactly, you know exactly what is the method that will be dispatched there. And that's the way you trim and you improve your code. So after we're done with the optimizations, we proceed to implement, basically in the Java AST, implement the features. For example, If there are cast checks, like instance of, then we replace it by a call to some library function that actually implements the check, and so for the cast, and for the longs, and for the arrays. So these are the normalizations that we do. So we have one thing called the devirtualizer, which only devirtualizes overlay objects. So these are objects, JSOs are also called, strings and array calls. So basically, because we implement strings and arrays as native JavaScript constructs, we don't want to monkey patch their prototypes. So every call that goes to string, then it's devirtualized. So you call us, instead of doing string dot equals, it will be $equals string A, B. So that's the devirtualizer. So for JSOs, it's more complicated. It has to insert trampolines that check whether it's a Java object or not. Then we flatten the catch blocks because JavaScript has no types, so it has only catch O. So basically, we do the transformation in Java. Because there is a Java equivalent to the catch block with only one catch at the top. Instead of object should be throwable, but it's the same as, this is not really it doesn't need to be a completely legal Java program at this point. So we do that transformation in which we flatten the catch, and we do it by doing instance of checks. Typo. Long cast normalizer. So because we emulate longs, we need to make sure we need to intercept every place in which a long is converted from other or to other type. And some of those coercions don't have casts in Java. Like if you go from int to long, you don't need to say int long I. So we make it explicit. So this pass basically inserts these casts so that a later pass can just do the right traversal and replace all castings to long by the appropriate implementation. And that's done by the long emulation normalizer, it's called. So this one replaces all casts and operations in longs by calls to long lib, which is the implementation of all our long emulation. So let's go faster. And then there's implement casts and type checks. So this basically replaces our instance of and casts by calls to functions cast.java. So there is instance of and dynamic cast. There are several versions depending on if it's a string or a JSO. This is the pass that does that implementation. And then the next, so as you see here, basically we are removing Java features and replacing by calls to library to implement that feature. So the next one does the same for arrays. Arrays are kind of native-ish. We do some things non-completely orthodox with them, but basically we replace all the code. For example, whenever you do a set on an array to emulate Java, we need to check whether the argument can actually be assigned to that slot. It's the correct type, which JavaScript doesn't care. So we rewrite array operations so that they follow Java semantics by issuing calls to the appropriate library functions. And I think this last is the equality normalizer that decides whenever there is an equal, decides how to implement it in JavaScript. So in JavaScript, you have reference equality, you have content equality, so you have, depending if it's depending what equality in JavaScript is kind of like crazy. You can compare things to other things and it performs conversions. So this is the pass that makes the choice how to compare values whenever there is a Java reference comparison. Lastly, so this is kind of very specific pass. So basically, normally in Java you would have a get class for each class that you have. Normally, most of them are not even used. So basically, we get rid of all of them and replace all the calls to get class to reference the property class. That is a property on the object. So, and that, so we do special processes to make sure that we don't create class literals that are not used. So if you have a ton of classes, but you perform a get class in a few of them, then we know which ones are the ones that are referred, which class literals to keep, which ones we can just not have. And at the end of here, so this is not actually a normalization, but there are lots of operations in the JavaScript code. So if you looked at the code, and we'll see an example later, the types have some IDs. They can be integer. That's normally the case for optimized compiles. They can be string. So we have several options. And basically, up to here, if there was a type reference, like for example, the instance of operation has a parameter a type, that would be a special node that says this is a type reference. This pass will transform the instance of the type reference in the instance of, but the actual value. Like for example, if object is assigned to type 1, then we'll replace the reference to object for a literal 1. Okay. So then once we did all that, so we optimize the code. So this is where we get most of our benefit optimizing the Java code. Then we normalize it to implement the Java features. And now we are ready to write it into JavaScript. And the main pass for this, it's a huge file class, which is called generate JavaScript AST, which performs all the translation. And it has sub-passes. One thing I didn't mention, but it's worth mentioning, in the AST before, you may have variables at the same scope that are the same name, because everything is by reference, so it doesn't really matter. So for example, when we parse several, let's say you have Java code that has several blocks, and it defines the same variable in all the blocks. We actually don't care to rename them, so we will represent that as the variables. We will move the definitions to the function, to the method, and we will keep the names colliding. We don't care because all the references are already resolved and they're pointers to the variable object. But then when we load to JavaScript, we need to assign a name. So, and we use the Java names to get a nicer naming in JavaScript. So we have this visitor that before we generate JavaScript AST, we fix all the variables that are duplicated in every scope. So then there is this pass that tries to understand the JavaScript that you wrote in GSD to understand the reference there, where do they point to. It's a slight complex process in itself, but I think we are. So, and then there are some like little optimizations here that probably would benefit moving them out. So this one records classes, methods that go across classes, and if they don't, you can remove the static initializer that's always inserted for static methods. And this is the generate JavaScript visitor is the one that does the translation, actual translation. So this is what the JavaScript AST looks like. It's similar to the Java AST. So nodes are expressions and statements and program fragment because we have this code splitting notion. So there is the notion of scope. So now you have also names that have some scope. And the main things are like functions. So these are all values, like a function in JavaScript, a value, you can pass it, so it's represented as a literal. And somewhere, the statement is over there. Okay. So I'm gonna gloss over these. This is the one that I'm like out of time, right? 5 minutes. But yeah, we want to Q&A. So there is this pass that decides the scope pretty intricate. Basically, the idea is find each identifier, see what are the scopes involved of the references, so that when we rename, don't make collisions that are like harmful, or don't rename things that need to be the same into different things. And this is all about that. It's pretty complicated, but this is the interesting one. So then at the end of the JavaScript generation, you will have code that looks like this. It has the static methods at the beginning. For each class, you will have the static methods, the constructors. You will have a call to this define class. Basically, this sets up the prototype, and the define type has the type ID, which if you run in optimize will be a number, but if you run in super dev mode, in incremental it will be a name, which is much useful. The super types it can be cast to, and its constructors. And then, so the other thing is that once you call define class, the underscore variable will be set up to the prototype. So this is the definition of all the methods and fields for that class. And at the end, you will have the class literal for that class. This used to be at the end of the program. Now it's at the end of each class. And basically, it has the package, the name of the class, and what's the super class literal, because you can query, and what is the actual type ID for that. So and this is what the JavaScript program looks if you run it in pretty mode. You get something like this. If you run the compiler in pretty mode. So once you get the JavaScript AST, we do a number of passes. The interesting is that we do some optimizations, and the reason for that is that the JavaScript that is in the GSNI methods is not processed at all by our Java optimizations. So we do that in JavaScript. So we have a static eval, which is basically static evaluation and constant propagation. We have the normalizer that fixes things that are not proper JavaScript. We have the inliner that inlines JavaScript nodes, JavaScript functions. And then we have a pruner in JavaScript, and some passes that are sometimes people use them or not. So there is this duplicated function remover that coalesces functions that have exactly equal text, code text. Because in JavaScript, if you have a function that says this.a, it doesn't matter the type of this. You can use the same one for all the classes. If you have a getter, the getter for a would be the getter for a. It can be the same function for all the classes. But it complicates the stack traces, so people don't tend to use this one. So there's an option for turning it on or off. This one, fancy name, duplicate execute once remover, basically removes redundant class initializers. That's the only function of that one. And the last pass is the one that renames all the names into obfuscated names, so that's the namer, that produces the names that are actually printed in the program. And we have three namers, the pretty, the detail, and the obfuscated. If you're running with stack emulation, we instrument the code so that to keep a better representation of the stack. Code splitting, I'm going to skip. And I'm just going to talk briefly about the linkers. So after you get the JavaScript, and the compiler runs the linker phase. We call them linkers. Probably packagers would be a better, or post-processors a better name. Sorry. So the purpose of the linkers is to package artifacts and compiler output. There are three types of linkers. There are the pre-linkers, there's the primary linker, and there's the post-linkers. The pre-linkers are the first one that get chance to run, and they can consume and create artifacts. The primary linker is interesting one. It's the one that takes the JavaScript output and produces the actual files you see that you serve in your application. It's responsible for the selection script and creating the modules. And it can do, for example, the most common one, which is the cross-site iframe, it appends some lines, it encloses, it does some transformation, but it only sees the program as text. So they don't have a AST view of the program. And then the post linkers, these run after the primary linker, and they basically transform artifacts in a form ready to be emitted to disk. And there is the one that produces the SOIC reports, and the one that produces the symbol maps, and the source map, that's the symbol map linker. There's one that just compresses the output of the primary linker. So, and I think I'm gonna just finish it now. There's not much to talk about.